The section that never ends continues. Although I think we are getting to the light at the end of the tunnel and it's not a train, so that's good. A piece of wire is 6 meters long. Let's make that 12 meters long just for this particular problem. Is cut into two pieces. One is bent into a square, the other is bent into a circle. How should it be cut so that the area is a minimum or the area is a maximum? So you're actually asked to find both in this particular case. So a little bit different there. Let's see if we can't draw ourselves some nice figures here. You've got the length of wire, 12 meters long. And it's going to be cut into two pieces. So let's make some cut here. This distance is going to be, we'll call it X. And this distance would have to be the rest of it. You can call it Y for the moment if you want. But Y really is going to equal 12 minus X. So whatever you cut here, the rest of it's going to be our distance for Y. We're going to bend this into two shapes. The first shape is going to be a circle. And the second shape is going to be a square. And we want these to enclose either a maximum or a minimum amount of area. Okay, so not an amazing picture, but decent enough. Picture function. Now the function we're interested in is the one that represents the area of these two figures. So let's see, function is going to be area equals, well, it has two parts to it, right? The area of a circle plus what else? Area of the square, right? Area of the square. Now I got to think a little bit about what I'm doing here. Do I want to let this be part of the area for the circle, or this is going to be related to the area of the square? I think because a circle is a little bit more annoying to deal with, I'm going to take this X and wrap it up into the shape of a circle. So let's see, the area of a circle, that's just going to be pi r squared. And the area of a square, well, it's going to be the length of the side squared. So right now, I don't got a whole lot going. I got to eventually write this all in terms of one variable, X. Now, if I'm going to take that first piece here and wrap it up into a circle, so this much is going to be wrapped into a circle, I need to figure out what the circumference is. Or I need to figure out what the radius is. Right now, I've got the circumference. So the circumference of that circle is going to equal X is going to be 2 pi times R. So if I solve for R, I get X divided by 2 pi equals R. And all right, I can plug that in here. It's going to be pi times X over 2 pi squared. How about the area of the circle? Or excuse me, the area of the square? I got to work with that now. Let's call this side have length S, according to S squared. What is the length of that one side?
12 X. Oh, sorry.
Almost. Remember, you've got that side here, 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 and here. So that 12 minus 4x really gets distributed amongst all four of these sides, right? So S would equal 12 minus x over 4, or you could write it as 3 minus 1/4 x. Depends on you, kind of up to you. I think it's gonna be easier to work with in this form. So let's write that as 12 minus x over 4 quantity squared. And I think we got our goal of writing this as a function of just one variable. So let's write that as f of x, or well, we can call it a of x, I suppose. Let me squeeze it in here, a of x. When I square this out, one of the pi's is going to cancel because I have a pi squared in the denominator and a pi here. So it's going to be x squared over 4 pi plus 12 minus x squared over 16. So I just squared the numerator and squared the denominator. Okay. Again, this one's got a little bit of a nuance. It's going to be different than some of our previous ones. Before I work on the interval, are we okay with our function? Let's work on the interval. X is how much material we cut out from one end of the wire. What could X go between? 0 and 12, right? Now here's something that's a little bit different than our previous problems. Brackets or parentheses on the 0 and 12? You can actually do a bracket. Because if you're doing a 0, that means you're using all the material for your square. If you do a 12, then you're using all the material for your circle. So you can actually use the endpoints in this one, unlike some of our other ones. In the one case, you're saying everything's going to be for the square. In the other case, you're saying everything, all the material is going to be for the circle. So you can use those endpoints. Let me rewrite this one more time. I'll write that as 1 over 4 pi times x squared plus 1 over 16 times 12 minus x squared. You could FOIL that one out, but I'd rather not. I'd just rather differentiate it here. We'll play with it as needed. As far as the analysis is concerned, let's work with a prime of x. Well, the 2 and the 4 are going to cancel, so I'll be left with 1 over 2 pi times x plus the 2 is going to come out here and multiply the 1/16. The 2 and the 16 will cancel, so I'll be left with 1 over 8 times 12 minus x to the first power. That's the derivative of the outside. What's the derivative of the inside? -1. Okay. Let's see if we can't clean this up a little bit more. It's going to be 1 over 2 pi times x. If I distribute, let's say the -8, -1/8, it's going to be -12 over 8 plus x over 8. Of course, that does simplify a little bit, but I wasn't worried about that at that time. Let's set it equal to 0 and solve. So let's see. I'll move this to the other side. I'll have 1 over 2 pi times x plus 1 over 8 times x equals, let's put that in lowest terms, 3/2. You can factor out the x from here. So it's going to be 1 over 2 pi plus 1 over 8 times x equals 3/2. Whew. And finally, you want to divide both sides by this coefficient, so I get x equals 3/2 over 1 over 2 pi plus 1 over 8. Now this is a critical point. I don't know if it's a minimum or a maximum. I just know that it's a critical point. Since it took a lot of work to get here, let me pause for a second. See if there's something you want to inquire about, or if you just want to catch up a little bit, that's fine as well.
Is it worth,
Rationalizing,
that, yeah,
was it worth what?
so like 3/2 over another thing, should you, like, is it?
You know, cleaning this one up, it's not gonna clean up very nice. I suppose if you wanted to, let's see, 3/2, 1/2 pi, plus 1/8. The lowest common denominator of all these so-called secondary fractions would be 8 pi. So I could multiply in the numerator by 8 pi, and then a denominator by 8 pi. And really that 8 pi over 8 pi is multiplying by 1. But if I distribute that instead of canceling it, I end up multiplying everything by 8 pi. And let's see what expression I get. It'll be a little bit nicer to deal with. The 2 will cancel in there 4 times. 3 times 4 will be 12 pi. This will cancel all together, and I'll be left with a 4 plus pi. So that might be a little bit nicer. I don't know if it was worth it for you personally in terms of the work, but that might be a little bit nicer to deal with. All right, let's continue. We need to check where this function has a minimum, where it has a maximum. And because we've got a nice concrete interval, let's just test those points. We're going to test the points at the endpoints. So let's see, x is going to be 0, and then 12 pi over 4 plus pi, and finally at 12. And let's see what the area is, a of x. Now for that, you're gonna have to plug that expression into your calculator. I'm gonna cheat a little bit and use the Desmos link that I've got for this. But the reason that we can get away with just this is because we've got a function on a closed interval. And it's gonna have to have a maximum or minimum at the endpoints or a critical point. That's coming back from section like 4.2 or something like that. Here's your Desmos link on this. So one way or another, as you cut bigger or cut smaller, you're gonna put more of your material towards the box or more of your material towards the circle. So at one endpoint, we've got 11.49459 as the area. So that's sending everything to the square. So 11.459. At the other endpoint, send everything to the square, we get 12. I might have this reversed from the way we set up our formula. Let me think for a second here. 0, yeah, this is backwards. Is that backwards? Yeah, because 0, this is sending all the area to the square, so the way we set it up, when x was 0, that'd be sending all the area to the square. So these are backwards, my bad. So that would be a 12. And this would be your 11.459. And the last thing we need to do is we need to plug in 12 pi plus, or 12 pi divided by 4 plus pi. Let me do that here. 12 pi divided by 4 plus pi. So about 5.278. Something doesn't look right.
That's it on the.
Oh, all right, there we go. There we go. Yeah, that's better. So 27.78, is that a 727? So this would be your max, and this would be your min. Nice, nice. All right, let's see. I think we've got one last one to do to put this section to rest. And again, I'm trying to show you some of the practical ways we can do this. I think you guys know that I brew my own beer at home. So fortunately, I don't have to put it in cans anymore. Sigma Pale Ale is the name I gave to my first beer. But maybe I wanted to design an environmentally friendly can. So something that doesn't require as much material. So that's what we're going to work on next. Now, if you have a can that encloses 12 fluid ounces of fluid, then allowing a little bit for space up at the top, that's about 23 cubic inches or 22 cubic inches. So what we're going to do is we're going to try and design a can that has the minimal surface area that still encloses 22 cubic inches of space. So that's our goal here for this last one. So design a can to hold 22 cubic inches of fluid. And really it's 22, it's fluid plus a little bit of airspace at the top. So the can should have minimal surface area. All right, so let's work on that. So here's our can, and we don't have much to go on right now. It's some height, and it's got some radius. Does anyone remember the formula for the volume of a cylinder? We talked about this the other day.
Pi r squared height times height.
Yeah, it's just the area of the base, which is pi r squared, times the height. So we're going to use that off to the side here. Volume equals pi r squared h. So we're going to need that. But what I want to do is I want to figure out a formula for this, my function. So I have to account for the surface area. What's the surface area? Surface area. And really there's two parts. Now I'm assuming that I'm making a can with a lid. If I'm making a can without the lid, that would change the dimensions a little bit, but the overall idea is going to be the same. The surface area is made up of two parts. The area of the lids, or the area of the ends, plus what else? Yeah, the area of the side. And very perceptive of you to call that the area of a rectangle. Now, consistently today, when we do this part, I always start it out in English. I don't try and do everything all at once. You don't want to try and formulate this in exact expressions right away. Do it in little pieces. Area of the ends. What's the area of the ends? 2 pi r squared, right? And as far as the height is concerned, the height requires a little bit of a trick here. So I know that this can is h tall, but I need to know, well, how far is it around? And here's my little trick. I'm going to take my can and I'm going to cut it. Let's just cut it down the side like that and lay it flat. So now finding the area of the sides is really finding the area of a rectangle, right? It's going to be the height times this top. But the length on that top really comes from the circumference of my can. So let's write it down this way. It's going to be h times the circumference of this, which is going to be 2 pi r, like that. Okay, looking good so far. Except one problem. Let me just call this S. I can't call it S of R because right now it depends on R and H. How am I going to get rid of that H? Yeah, find the H with the volume. All right, so the volume was 22 equals pi r squared. H, so that means H is 22 over pi r squared. So that's H. And now I can plug that into my formula. It's going to be 2 pi r squared plus 22 over pi r squared times 2 pi r. One of those r's is going to cancel. The pi is going to cancel. The 2 is going to be multiplied by the 22. Finally, get out the oxygen bottle. I can finally give myself a nice little formula, 44 over r. Whew. Let's think about the interval. You could make this can really wide and very short, or very narrow and very tall. There's a trade-off in between. But as far as the interval is concerned, it starts at 0 and goes to infinity. Okay. Let's see. Well, picture function interval analysis. Let's work on that part. And as far as the analysis is concerned, let me rewrite my function just a little bit, make my life a little bit easier. Any suggestions on how to rewrite this? Yeah, thank you. A couple voices there. Write that as 44r to the negative first. What does that avoid that makes our life easier? Quotient rule, yes. So we're avoiding the quotient rule. A prime of, or it's going to be S prime of r is going to be 4 pi r minus 44r to the negative second equals 0. We're going to play the same game we did with our previous problem. Let's see, set that equals 0. I'm going to kind of cut to the chase. Really, you're dividing by r squared. So to get rid of that, I'm going to multiply everything by r squared. R squared times 0, of course, is going to be 0. R squared times r to the negative second. Add the exponents, I'll get r to the 0 power, which is just going to leave me with a 1 there, times 44. R squared times that gives me an r cubed. So 4 pi r cubed minus 44. If you solve for r cubed, it's going to be 44 over 4 pi, which of course is 11 over pi. R is going to equal the cube root of 11 over pi. So kind of a strange number there, but that's the correct one. So that's the radius of your can. Let's actually figure out what that is. The radius equals the cube root of 11 over pi. And then I'll also figure out the height. For this one, I'm going to go back to my calculator. Let's clear out a bunch of stuff here. Just a quick reminder where you can find the cube root that's going to be underneath the math menu. So math, and then the fourth option down is your cube root. And I'll get really fancy here. I'll hit the alpha key, then the y equals key. This first option allows me to do a fraction like this. 11 divided by pi. And I'm gonna take this and store it in X, because I'm gonna need to use this to find the height. But take note of the actual radius there. Times 2 for the diameter, so about 3.037 inches for the diameter. Let's work on finding the height. For the height, I want to do this fraction, so alpha y equals again 22 divided by pi x squared. And there's something interesting that happens when I do this, when I compute this. Does anyone catch what was interesting that happened? Basically, I'm trying to see who's able to get this number. Are you getting a similar number there? No? No one's got that? Has anyone got that?
I have the same thing.
Yeah, you should get the exact same thing. So it's interesting. Basically, the diameter and the height are the same. And if you wanted to see what that would look like, let me share it with you. Because I had a neighbor a long time ago who was a World War II veteran, and he had this killer wood shop. And he built me that very can. And he said it was accurate to within a 10,000th of an inch. I don't know, I think he's off a little bit, but I'm not sure. Anyways, there's that can. It has kind of a square appearance because the height and the diameter are the same thing, as opposed to this. Now, you're actually pretty close with this dimensions. So how come people don't use this dimensions for our pop cans? It's comfort. I'll pass these around. It's consumer preference. We don't like cans like this. As far as holding, it's a little bit too big. Can't wrap your hand around it as much. So let me pass it around. There's been a lot of engineering developments over the years that's reduced the amount of metal that you need to take to produce like 1,000 cans from around 38 pounds per 1,000 down to like 32 pounds. And of course, the best answer is recycling. So, but consumer preference has a lot to do with this. So that's probably why they haven't done this. And of course, it will require lots of retooling. If you look at your cans of corn and other things like that, Fresh Like Corn, when you go to the supermarket, you'll see Fresh Like Corn is packaged in cans with that dimension. They're kind of square looking. And they're doing that to save metal. Comments or thoughts? All right. Whew. We're done.